My name is Eric Marshner. I'm the verification architect with Mentor Graphics, and I'm the organizer for this session. I'm sure all of you are familiar with some of the challenges that are coming up with regard to low power design. The obvious ones are consumer demand for products that use less power at the same time as having more functionality, longer battery life, producing less heat, etc. This is exacerbated by the technology trends that we're seeing. As feature sizes get smaller and smaller, we're having more difficulty managing power because of static leakage in particular. And this is getting worse and worse as the technology evolves and gives us better performance and higher capacity, etc. So power is becoming a dominant concern. Modeling what goes on with power management is also a difficulty in that the hardware description languages that we use traditionally don't understand power. They don't model the effects of power. Hardware description languages have always assumed that power is on when you start, and it stays on, and it's on throughout. So modeling the effects of power management is something that we have to add in on top of what hardware description languages usually do. And of course, power management adds complexity to the design. So that leads to more potential for functional errors, more requirements for verification, and a need to do verification earlier in the process. The unified power format is a standard format for defining power intent that was originally developed under Accelera and has evolved further under the IEEE. And as an extension to TCL, which is a common tool control language, it's syntactically fairly familiar. It's easy to use from that perspective, and it can be used in the context of TCL programming, so you can do general scripts, etc. As I mentioned earlier, it's enabling verification of your power intent early, and also driving not only verification but also the implementation flow. And we'll talk more about that as we go through the presentation today. The presentation today is coming to you from members of the IEEE 1801 UPF working group. This is the group within the IEEE that has been developing the standard since 2007, I believe. The 2009 standard is out and has been in use for a long time. There's a new version coming out shortly. It's done and in the approval process now, and you'll hear more about that today.
My name is Jeffrey Lee. I'm a corporate application engineer with Synopsys. And I'm kind of giving you the spiel for what is power intent to be considered for doing your functional designs. So the first thing that usually starts out as, well, what's functional intent versus power intent? Right? You guys are used to designing your chips in VHDL, Verilog. Some of you perhaps system Verilog. We won't ask for any system C folks here. But the point is, for those you know, hey, I'm building a particular chip with a particular set of functionality. Now, when you start bringing in power management, how does this mesh in here? Is it really part of your state machine for your functional intent? Or is it really part of your power intent? Here are the things that belong in your functional intent, and by the way, here are the things that we would introduce you to club into your power intent. You're all familiar with the functional intent. Your state machines, is it a DSP, cache, whatnot? What might be somewhat new is for the power intent, right? Your power distribution architecture. Right? What's a power domain? How are you defining supply rails? For most folks who are doing RTL design, having to worry about what's the name of your VDD seems a bit far-fetched. It's usually, hey, I've got this, it works, it's always on. This is something the physical guys take care of for me, right? They worry more about, oh, this trace won't meet here. We, for RTL design worried, hey, does this functionally work? But for some of these things, we need to bring some of this information forward into RTL design to properly model how your design works with this power intent. And there's things for power strategies, right? Exactly what are the states of your design? Just like your finite state machine for your chip, you have a particular set of operational states for your designs for power intent. And then, most importantly, we've got some special cells that I'll be going over, and these are going to be the bits that help keep everything together and work well. Power intent, basically captured in UPF, your other stuff captured in RTL. So, starting off then, what's a power domain? Power domain is pretty much defined as a collection of instances, and we're going to treat these kind of as a group for power management purposes. Now, you'll notice here I've got power domain for the top, power domain for this block, and a power domain for this group of blocks. What this is telling you is that you don't really have to keep a strict one-to-one correspondence between a logical hierarchy and a power domain. You can have multiple logical hierarchies belong to the same power domain. But the key is a power domain is a grouping of logical hierarchies. Building on that, we have our power supply network. This is basically how you guys are getting the power from one point of the chip to another point of the chip. If you have a supply up in the top level that you need to bring down so that another block has power, this is what's defined in your power supply network, and this is a logical representation. So even though physically something might not go this way, logically speaking, to get supplies from one area to another, needs to come through. This is also where we'd have an abstraction to say, hey, this is an interrupted supply, this is a power switch. So for this particular grouping, I actually have the ability to remove power, to save power when I don't need this particular group of cells to be active. I said, we had these power management cells to kind of glue it all together. Well, kind of glue together, probably too rough a term. But why do I say glue together? Well, we have level shifters, isolation cells, retention registers. We'll focus on level shifter and isolation cells. These are the ones that are going to make sure that whatever ones and zeros you want to pass from one group of cells to another group of cells makes it there in a fashion that is still recognizable. So, if, getting ahead of myself, but if you had a 0.7 volt 1-tick B1, that doesn't necessarily mean it translates cleanly into a 1.2 volt 1-tick B1. So what a level shifter will do is make sure that you have the proper signal levels, so the functional one that you want represented is actually properly represented in the circuitry. Isolation cell basically just says, in case of interruption, I want to make sure that a known good value is being sent from one particular domain to another. So these are going to protect unknowns or X's from propagating in your designs, because it will clamp and give you a known value. This way, you have a known state. And retention registers are basically sequential cells that will maintain their state despite the fact that external power has been removed from the domain. And we'll talk really quickly about some power management techniques, namely power gating, multi-voltage, and DVFS, dynamic voltage and frequency scaling. Power gating is just simply, hey, let me turn off power for a specific group of cells, thereby saving power by not having to maintain any particular active states, and allow me to move on through. So simply like for most of your smartphones, you put it in your sleep mode. Well, a good portion of that phone circuitry went to some sleep state. Some of it may have actually been powered off altogether. Right? This is going to give you some of your actual power savings by not having to keep multiple portions of your circuit powered. And it's enabled by what we call power switches, or as some folks like to call them, empty CMOS cells. And then we move on to multi-voltage. This is basically saying, hey, I've got a design, and instead of you, the designer, trying to manage each of these by hand, which I believe some or most of you have done in previous designs, you can do it in a more automated fashion by saying, hey, I've got a design, and I've got discrete voltages for different portions of the design. And the tools themselves will automate and take care of making sure that all of these are operating at these voltages, have the proper signal levels passed through. This way you're not looking at trying to do your own homegrown hodgepodge, right? This is to enable you to have more automation to get this multi-voltage design. And then also we have the concept of a bias voltage, which some folks are using. This is basically to change the threshold voltage of a cell. So as you know, that if you want to make a cell less leaky, you could lower the voltage a bit. If you wanted it to be faster, you can increase the voltage. Bias voltage is one way of doing this. And finally, dynamic voltage and frequency scaling. So this is a power management technique where you basically run through and say, oh, while on the fly, let's say I'm operating at a specific state, and you hit a particular state and say, well, instead of being at 0.8 volts, because someone tripped a video on their smartphone, I'm going to move up to a 1.2 volts so I can actually operate faster and provide the performance. So dynamic frequency voltage scaling is basically saying, hey, let me try to model all the different voltages and on the fly say, oh, I can change from one voltage state to another voltage state without actually having to go through some of the other little details. So this is an abstraction to say, hey, you can pull this together for your simulations and your implementation. Power management architecture. So we'll cover power station transitions, isolation level shifting, state retention, basically, those special cells. As I said earlier, isolation cells basically to protect one group of logic from another group of logic. So if the purple logic here is powered off, you don't know what logic values are going to propagate over into this orange group. So what the isolation cell does is give you a known value, either the last known value or a 1 or a 0, depending on what you choose. This way, you have a known state. Level shifter, as I said earlier, just basically make sure that the 1s and 0s that you're passing from one group to another are actually properly understood at the proper voltages. And then state retention is, again, hey, I've got a flop that can save its value despite that the power for the area has gone off. This way, when you restore the power, you don't have to spend as many cycles restoring. You can just say, oh, power's up, everything's stable, and we're back to the last known state. And to tie it all together, basically, we've got a few different design styles, multi-voltage with no state retention and shutdown, and basically level shifter, so you can kind of see, oh, my next chip, it's going to be multi-voltage with shutdown. You're going to need to look at level shifters, isolation, power switches. So it's a quick, handy-dandy cross-reference for you to say, here are the things that I'm going to need in order to implement my next design.
This presentation is going to go fairly deeply into the language constructs, the commands of UPF. We're going to try to cover a lot of material fairly quickly, in part because UPF has been around for a while. It's gone through a couple of different versions, and so it's kind of an archaeological dig in some ways, looking at commands that have been developed quite a while ago that are still present, new commands, and new commands that are coming on top of that. So what is UPF? As I mentioned, it's an evolving standard. First came out in 2007 with what was called the Accelera UPF standard. This is also referred to as UPF 1.0. And then in 2009, the IEEE version was developed. That's referred to as 2.0, and it includes essentially all of 1.0, so it's a superset. There is a new version that's been developed. It's been submitted to the IEEE for ratification, and that approval is expected to come next week on March 5th at the RevCon meeting. So it's imminent at this point. It's a standard for modeling power intent, to define power management with the main goal of building in the structures necessary to minimize power consumption, and in particular through control of leakage. It's based on TICL, so it uses TICL syntax and semantics. You can mix it with non-UPF TICL, so you can write scripts based on TICL that include UPF commands. And of course, it's also based on HDL semantics too, because you're layering this on top of the design information in your hardware description languages. It's intended for verification of various sorts, dynamic or static, and also for implementation, to drive the implementation process. And the reason is you want to make sure that what you're verifying and what you're implementing are the same thing. You wouldn't want to go off in different directions. The typical flow that we envision here, and this is actually captured in one of the previous UPF specifications, is that you start out by adding UPF to an RTL design in order to specify what you're going to do in the implementation process for managing power. You haven't done that yet in RTL. The RTL is a very abstract description. But by capturing this information in UPF and attaching it to the RTL design, you can now do things like verifying that the RTL is going to work when you do the power management implementation, rather than just looking at the abstract model and verifying that it works as if power is always on. Okay. You can then use that same UPF to drive the implementation process through synthesis, place and route, DFT, etc. And all along, use UPF together with the netlist that occurs at a particular point in the flow to, again, verify that the netlist plus UPF is still working correctly as you expect it for power management. This is an oversimplification, obviously, but the point is that UPF is capturing the power management plan that you have for the implementation early enough so you can do early verification, you can drive the implementation process, and you can use that information at various stages in the implementation flow to make sure you're staying on track. So this next section is a really quick overview of what the commands are in UPF. We're going to start off with the Accelera UPF definition, and it created commands in the following areas. First of all, for navigation, to move around in the design in order to sort of change the focus and change how you specify what to do in different parts of the design. There were some commands that had to do with building the supply network. This includes creating ports, nets, switches, and doing connections. There are commands that have to do with defining power domains. And as Jeffrey mentioned earlier, a power domain is essentially a set of instances that are powered in a similar way. And so you have to go through your design and carve it up into these subsets, each of which is going to be powered in a particular way. We also want to talk about power states. For each one of these sets of instances, for each one of these power domains, all of the instances are in a particular state. They may all be in a sleep state. They all may be in a normal active running state. May all be in an off state. We have to characterize these because we want to think about the behavior of the designs, in particular in verification flow. There are a set of commands referred to as strategy commands, which are all about determining where to insert level shifters, isolation cells, and retention registers. As Jeffrey was mentioning, these are sort of the glue that make the power domains interact well and deal with power domain effects such as powering down and powering up. You do need a connection to the implementation flow, and so when you are doing implementation based on UPF, there is often a requirement for giving some more information about which cells to use out of the library for isolation, for level shifting, etc. So there's a set of commands called map commands to do that. There are a few commands that I've characterized as HDL interface. These are ways of dealing with the fact that you're interfacing between UPF and a hardware description language, whether it's Verilog or VHDL or whatever. We're not going to talk much about those, but there are a few commands in that group. And then there are some commands that have to do with code management, essentially, loading files, etc. Again, I won't cover that much, but you can think of that category as existing. Now, this is the Accelera version of UPF as of 2007. What's happened since then? Well, the IEEE took the standard, the next step, to develop IEEE 1801-2009. And of course, it started with the Accelera standard and added things to it. The stuff in purple here is the new stuff that's in the 2009 standard. And this is referred to as UPF 2.0. So chief among the new additions is this notion of supply sets. We'll talk more about what supply sets are, but this is the central change from the Accelera standard to the IEEE standard. It's a more abstract model for how you represent the supplies that are provided to different power domains, to different cells in the design. And it enables a lot of the other capabilities in IEEE UPF. In particular, it led to a new way of defining power states, which we'll get into it later, but it allows you to think about the problem of power intent specification in a much more hierarchical fashion. That's the key issue. It also led to the creation of something called sim states, which are ways of modeling the behavior associated with power supplies, and provided a new set of behavioral modeling capabilities that weren't present in the previous version of UPF. It also allowed us to talk about attributes of objects, namely the driving and receiving supplies of the pins or the ports of a cell or a macro or whatever. This is something that you didn't have the ability to talk about in UPF 1.0. In 2.0, you now have the ability to talk about these characteristics, and that enables a more complete flow from the point of view of dealing with the kind of practical issues that come up when you're doing design and verification. Another limitation in 1.0 was there wasn't any way of defining control logic. 2.0 now adds commands for specifying control logic. And there are a few other things. Create composite domain here. There's a way of putting domains together after the fact. If someone defined two different domains, but you don't think you really need two different domains, you just want one, you can compose them. There are other capabilities like this set retention elements command, or use interface cell command, which is a generalization of the map commands, and some other code management commands. So again, we're not going to talk about all of these in detail, but what I wanted to do was give you the impression of what does UPF encompass. Well, this is what 2.0 encompasses. And 2.1, the next version of the standard that's coming, will add a few more things. Not a whole lot, but as you can see, there are some commands for defining power management cells and some additional code management commands and a couple of new commands here, set equivalent and set repeater. We're going to cover these towards the end of the presentation today in a fairly brief way. You may also notice that there are some commands that have been grayed out now, and that's because in 2.1, certain commands that are left over from the earlier days have been deprecated or identified as legacy commands, which are not recommended any longer. So as I say, UPF is an evolving standard. It's gone through almost 3 complete development phases now. And what we're going to focus on today in this presentation is what you can do with UPF 2.0. We'll also talk a little bit about where 2.1 is going to add some value. The next section is going to go through some of the basic concepts in UPF, and it's going to be focusing on the capabilities that you got with version 1.0 of UPF. The reason we're doing that is that that's a good starting point. It's not that that's the best use of UPF today, but that's a good starting point, and then we're going to build on that to talk about the 2.0 capabilities. We think in terms of the logic hierarchy in the HDL design, because in UPF we're specifying power intent for your design, and we have to apply it to the structure of the design, which is typically a design hierarchy or a number of modules instantiated in each other, etc. The term design hierarchy in the HDL context encompasses a lot of things. It encompasses any kind of hierarchical structures, including things like subroutines defined inside of packages, generate statements defined inside of blocks, etc. In UPF, we have a slightly more abstract idea of hierarchy. We're only looking at the hierarchy of instances, and that is usually called the logic hierarchy in the UPF spec. So I'll be talking about logic hierarchy here, and I mean the instance hierarchy, in particular, not talking about generate statements, other nested internal blocks, by and large. The key idea with UPF is that the commands that you write in a UPF file are interpreted in such a way that they add definitions to your HDL, and they add definitions within the scopes of the HDL design. So if I have a command in a UPF file that says create a port, it creates a port with that name in a particular location within the logic hierarchy. And I've shown that with the orange box. That's the current scope, and that's where that command within the UPF will be applied. If I change the scope and then execute another command, it may create an object somewhere else in the hierarchy. And the important point here is that depending upon where you created things, the name that you use to reference that object is going to be declared in that location. It has to not conflict with names that are already there, obviously. And also, just like any other name that's defined in your HDL, you can refer to that by that name in that location, or in general, with a hierarchical name that goes down to that location, and then you refer to that object. So think of UPF as essentially overlaying names on top of your logical hierarchy. That's the fundamental concept. A related question is, does this hierarchy that we're working on represent the ultimate implementation in terms of the floor plan? And the answer is, it depends. Some people really like to think that. They like to keep the logical hierarchy in their HDL aligned with the way they're going to implement it in the floor plan. And the reason is that gives them the ability to control some aspects of the floor plan and the routing and powering of things, etc., by working at the logical hierarchy level. Others would prefer to leave that all to the tool and not conceive of this logic hierarchy as being reflection of the eventual floor plan. UPF supports both models, and the only error here is to assume that it's always one or the other. It could be either. Just be aware that you can think of it in either way. Okay, so navigation. We talked about navigation commands. Bear in mind that the design that we're navigating over might actually be part of a simulation environment, in which case there might be more than just the design. There might be a test bench and other simulation structures. So one of the questions is, where do we start? The set design top command in UPF identifies the top of the tree that we're going to work on. And then within that, we have the ability to move the scope around. This is a little bit like change directory in Unix. You can set the scope to an instance that's somewhere down in the tree, set scope P1/M1. You can set the scope to the parent, pop up a level and down a different path, or you can start at design top and by using slash, go directly to somewhere else in the tree. This is just a way of localizing what you're going to do within the design as you apply UPF commands. And in the coming diagrams, I'm going to use this orange box around the module that is assumed to be the current scope. I'm not going to talk about scope much anymore. These are all instance names that we're talking about here. There is an assumption that at the top of your tree, the module name is also an instance name. Okay, so Jeffrey talked about creating power domains, partitioning the design up into collections of instances that in each set are powered in the same way. So there is a UPF command called create power domain, which effectively creates a set. And the way I'm showing that here, just so you understand, is here's the hierarchy. You can think of this as the HDL design existing separately from what the UPF is constructing. Here is the power domain that's been constructed in it. And the power domain has a name which has been declared up here in the current scope. Remember that. The power domain name is PD sub. But the contents of this set, in effect, include all of the instances in the entire logic hierarchy. And the reason they do is we use the -include scope option here, which basically says, from where I am all the way down, include everything in the power domain. So you can see that the name is sub/PD sub because it's actually declared inside of instance sub, and there's the name that was created. So we can do this again and carve out a sub power domain out of some of the components that were put in that original set, and do it again and create another power domain that has been carved out of the set of instances in the original power domain. So one point here is that you can, in effect, override the creation of one power domain with the creation of another. You can carve out lower portions of the hierarchy in a power domain and put them in a different power domain. Just to complete, we'll do the same thing on the other side. And the key point is that for all of these, the names that are created when you run this create power domain command are created in the current scope. So all 5 of these names, PD sub, PD proc1, PD proc1 mem, etc., are declared in sub. This is a possible point of confusion, so I want to make sure it's clear here. Even though they seem to be hierarchically nested below, it's the nesting of subsets that you're looking at below. All of the names are declared at the top level. The way I showed you to partition the example here in the last slide is not the only way it could be done. There's another way to partition it, and that is horizontally. We can just divide it up into 3 power domains, one at the top, one in the middle, one at the bottom. I'm going to use this one for simplicity in a number of the remaining slides. But again, any way you want to define the power domain structure, it's up to you. This is where your creativity comes into play in order to minimize and optimize the power. So we talked about power domains, but power domains have to be supplied with power. The supply network commands in UPF allow you to do that. So we can create supply ports with the create supply port command with directions and names, VDD, VSS. And as before, VDD and VSS are going to be declared in the power domain associated with sub. I'm going to show them up here rather than in the sub box, but essentially they're declared in the sub. We can create supply nets associated with this power domain, PD sub. And there they are, power and ground. And we can connect them using connect supply net. So now the power is connected to VDD and ground is connected to VSS. The interesting thing is we want to make sure that those power supplies are powering the instances that are part of this domain. So what we're going to do is use the command set domain supply net, which says that for PD sub, the primary power net is power and the primary ground net is ground. And what that does essentially, it's extended those supply nets into this instance that's inside of this power domain. Effectively, the primary supplies of a power domain are implicitly connected to every instance in the set of instances that's part of that power domain. And this is how we connect the values on the power ports, the supply ports, to the behavior of the elements in that power domain. In simulation, we'll change the behavior of the elements in that power domain based on the status of the supply nets. That's the essential idea about power-aware simulation. There's another capability called reuse that allows me to extend the use of those same supply nets that I've already defined for use in a different power domain. These were defined for use in the PD subdomain. Now I want to use them in the PD proc domain. So I can act as if I'm creating new ones, but I'm going to use -reuse, and that just extends the ones that are already declared. Remember that these are all declared in the current scope. So in fact, I'm not creating a new object with that same name. That would be a conflict, in fact. But I am making that same object available in a different power domain. So reuse allows us to do that. And then, of course, we can set the domain supply net for these as before and extend them into all of the instances in the PDProc domain. Now, suppose we have a supply network that involves an internal switch. In this case, what we want to do is create a power switch on one of those nets. And you can see that I've created this switch here with a switch control signal, and it has an output. I need to have that output defined, so we actually need to create supply net for this domain PDProc and give it a name of this switched output. And that switched output name has been used as the net to which the output port of the power switch has been connected. You don't have to put switches only on power. You can also switch the ground. In some cases, that's the way people want to implement their circuits. So you can do it either way. But one critical issue with 1.0 is you have to have the power control already in your design. There's no way in UPF 1.0 to add control signals. So one limitation here is that if we're going to use SW control as the control for this switch, and here's the references to it, it's the control port and the expression that controls whether the switch is in an on state or an off state. Unfortunately, you already have to have that in your HDL, which kind of goes against the grain of using UPF on top of a design that is power agnostic. You'll see that we fixed that in 2.0. And as before, you set domain supply net to now power all the instances in this power domain with the switch supply. It's possible that you have a supply that is not switched internally, but you know it's switched externally. You might even have a control output that tells somebody externally whether to switch it or not. Well, in that case, you might want a different supply port, so we've created here. And we're going to reuse this and use it to power the instances in the PDMEM domain. I won't go through the details, but it's much like as before. We're creating a port. We're actually not creating the supply net in this case, but we're connecting them all to the instances. This is a special case. You can actually refer to a port like that, VDD2, in a place where you would expect to find the name of a net. And in UPF, the semantics are such that you can just sort of implicitly refer to the port as if you had created a net with the same name and you're using it directly. So kind of a nit, but something that gets in the way sometimes. Let's talk about the states of the supply ports now, which is getting to the next step of how do we know how the various parts of the design behave based on the state of the supply. So in this case, we've got an always-on supply, VDD, and we model it using add port state, which says, here's a name on 1.0 for a state of this supply port, VDD. And it's what we're saying is that it's on with a 1.0 volt supply. Here's a similar statement for an internally switched supply. And in this case, I'm referring to the port that's the output port of the switch. And I'm saying that there are two states. There's an on state where it has the voltage 1.0 and an off state where it's off. In this case, this is the externally switched supply. Notice we also have an on state and an off state. And the voltage is actually different. In this case, it's 0.8 volts. So this is externally switched, obviously, because if it can be in both of those states, but there's no switch here, the switch must be outside. Now, this is a little oversimplified. In reality, every supply can be switched, and one of the questions is, should I model all of my supplies with an off state always? That gets into subtleties I don't want to deal with here. But I'm trying to make it clear that you can model the states of a supply and imply from that whether they are switched, whether externally or internally. The last one is the common ground. It is in an on state because it's connected, but the voltage is 0. This is an important point. 0 doesn't mean off. It just means that's the voltage with respect to some hypothetical reference voltage. The state is what determines whether it's connected or not and whether it's going to be functional or not. Essentially, we've said that there are multiple states for a couple of these and single states for several of these. So if you look at it, these are the sets of states that we can have for the various supply ports, and in this case I'm referring to the switched supply net as opposed to the output port of the switch, but they're equivalent. And if you take a close look, you can see that VDD is the main supply for the PD sub domain. The VDD SW is the main supply for the PD proc domain, and the VDD2 supply is the main supply for the PD-mem domain. So in effect, these supplies correspond to the domains. And if we want to think about how the system is operating and what states the system can be in, what we want to think about is what are the combinations of these possible states of the supplies that are legal. And we can do that by essentially expanding the table and looking at the various possibilities that we want to consider. So in this design, we're going to say that there's a normal case where the PD sub supply is on at 1.0 volts, PD proc is on at 1.0 volts, PD mem is on at 0.8 volts, and the VSS is on at 0 volts. That's the normal case. There's a sleep case where it's much the same except that the PD proc domain has been turned off. And then there's a hibernate case where PD proc and PD mem have been turned off. These are the combinations that are of interest to us. These are the combinations we think we're going to put the design into in addressing the various system scenarios that we want to put this design through. So can we describe this in UPF? The answer is yes. We have commands called create PST and add PST state. Create PST essentially creates the header of a table like this. You can see VDD, VDSW, VDD2, VSS. That's the header. And add PST state allows us to specify those three states in terms of the values of the corresponding supplies in the header. So this set of commands up here is identical to this table. Jeffrey mentioned retention, isolation, level shifting. Once we've defined the power domains and the powering of those domains, then the question is, well, how do they interact? And this can be seen to quite an extent by looking at this power state table. I'm going to show you in terms of the graphic rather than the UPF, but you can think of this as representing the UPF power state table. So if you notice, we have PD proc, which is off in certain cases. And in those cases, we may want to save the state of the registers in that domain so that when it comes back up, when it gets turned back on again, we can turn it on very quickly, as opposed to taking a long time to reinitialize. If we do that, we want to use the set retention command, which essentially says add retention to some or all of the state elements in this power domain. And in this case, we're adding retention registers to P1 and P2 and powering them with VDD and VSS. This is upstream of the switch, because the power for retention registers obviously has to stay on in order to keep the state alive. You can't power it with a switch supply if the switch is going to be turned off. In addition to this, in UPF 1.0, you also specify the control signals that tell when the state retention registers are turned on or turned off. And in this case, there's a single signal SRB, which is used as both the save signal and the restore signal, different edges, obviously. And that's shown here. But as before, that signal has to exist in your HDL. So again, this is a limitation of 1.0. You have to have the signals already defined. Now, there are other places where some power domain is off. Do we have to put state retention everywhere? No, it's up to you. It's your decision whether you want to reinitialize or reset everything every time you come up, or whether you want to retain state, do partial state retention and a mix of state retention and restoration. It's really up to you. This is part of the design process for designing the power intent. For isolation, we have the case also where this power domain is off, but another power domain that it interacts with is on. This is a case where you want to protect the power domain that's on from possible errors resulting from being connected to power domains that are turned off. So here we use a command called set isolation. This is being applied to domain PD proc. That's the one in the middle. And we're also going to need a set isolation control command in this case to specify the control signals. In this case, we're applying this to the outputs of PD proc. So we're talking about the output ports up here of these instances in PD proc. And we're going to put the isolation cell into the parent domain above the cells that have those outputs. So in this case, that means putting them up here in the PD subdomain, attaching the control signals specified in set isolation control, and running the power in as before. And of course, once again, the control signal has to pre-exist. Now, it's also the case that PD proc, when it's off, is connected to PD mem, which is on, and so we need to think about isolating that boundary as well. course, the ports that we have to isolate here are not in PD-proc, they're in PD-mem. So in this case, we want to write an isolation strategy and a set isolation control command as well for the power domain PD-mem, which is the one on the bottom, because we want to put isolation on these points where there's an interface between this domain, which is on, and the PD-proc domain, which is off. In this case, we're going to isolate the inputs to the instances of PD-mem because those are outputs of the above domain. And we're still going to try to put them in the parent domain, which is to say the PD-proc domain where P1 and P2 are. And so you end up with isolation here, and I'm not going to bother trying to show the control signal. Now, one point to notice is that if you put isolation in a domain that's turned off, and the goal is for that isolation to protect other domains when that domain is turned off, then those isolation cells clearly can't be powered by the same supply as that domain, right? You have to have backup power for those cells. And this gets into a whole discussion about what kind of cells you have in your library and whether you want have single rail or dual rail cells and all kinds of stuff I'm not going to touch on. But it's one of the reasons why it's important to think about the location in which you're inserting isolation cells. And so an alternative is to do the same thing, but instead of putting the isolation on the parent, we put the isolation in the self here, and that ends up putting them inside the PD-mem domain, and now they can be powered with the regular power without a need for a backup supply. We have level shifters as well. Here's a case where we've got an interaction between PD-proc and PD-mem when they're both on, and they're on at different voltages. So we have to shift the values going back and forth. And you do that with the set level shifter command. There are a bunch of options here. It applies to domain mem in this case because we're going to put it on the inputs to the memory side. There's a threshold option that allows you to tune whether level shifting cells are inserted if there's just a tiny little bit of a difference in the voltage or whether it takes a larger threshold to cause them to be inserted. You can apply them to both inputs and outputs or individually one or the other. You can control whether they're applied depending upon the direction of shift. There are various options here. I'm not going to get into it. And of course, the location option is much like you saw with isolation. One thing that is different here is that in UPF 1.0, there was no provision at all for providing power to level shifters. There's sort of an implicit assumption that level shifters would be powered by the same supply that's driving in and the same supply that's driving out. That's changed in 2.0. And since they're just level shifters, there's no control, so there's no issue about control signals existing. So that was a quick overview of 1.0 UPF. That gives you the capability for specifying the power intent for partitioning the design into power domains, providing the supply network, and sticking in the interstitial cells that make the whole thing work. So what do you do with all of that? Well, you can verify the design, and you can implement based on that UPF. Verification, just to add a little bit more detail, involves typically running simulation or some kind of dynamic verification. Of course, there's also static verification. I won't touch on that here. But when you're running dynamic verification, what you want to do is set up those supplies so that you can observe the effect of turning the supplies on or off, changing the voltages, etc. And there's a whole collection of semantics associated with UPF about corrupting signals if the power isn't right for them to operate correctly. I'm not going to get into great detail, but essentially you get to watch in simulation what happens if you don't give the required power for a particular part of the design. And in particular, what happens if you shut down part of the design without correctly isolating it or level shifting it or whatever in order to make it interoperate correctly with the rest of the design. The bottom line is that there's capability in UPF in a package that's delivered along with the UPF standard that enables a simulation to drive the power supplies that are distributed to the entire design through UPF. And you can turn the supply on, this particular supply, to 1.0 volts, turn it to 0.0 volts, or turn it off. And these supply on, supply off functions are the primary ones you'd use in simulation in order to control what's going on. Now, for implementation, you'd probably move to the map commands and use the map commands to help your implementation tools decide which cells to pull out of the library in order to implement the various aspects of the power management. Okay, so just to review, we talked about navigation commands, set design top, set scope. We talked about supply network creation commands, creating ports, nets, connecting them, creating power switches. We talked about power domains, the basic partitioning of the design into sets of instances, each of which has the same powering, and using set domain supply net in order to set up those primary power and ground nets for each power domain. We talked about power states. These are actually power states of ports, which then can be used in power state tables to model how the power domains themselves are operating. We talked about the strategies for inserting retention, level shifting, and isolation. And I haven't really touched on this, but there are some commands I mentioned: load UPF, save UPF, and then some miscellaneous commands. These are bind checker and VCT commands, or the part of the HDL interface set that I mentioned earlier. And we talked a little bit about map commands. That's more or less what you use when you're using UPF 1.0. I mentioned a couple limitations of 1.0. First of all, power supply concept. We're dealing with power and ground nets, but the only thing they can do is be on or off. And that doesn't really cover all the cases we want to cover. There was a discussion earlier about bias. That involves more than just the primary power and primary ground net, and it involves modeling that we can't really do in 1.0. So there's more work to be done here. Another thing that I skipped over, that last bullet under the first bullet, supply network must be defined to enable verification. This is really a key issue. In UPF 1.0, you can't do any verification at all until you know what the power states are. The power states are defined on the primary supply ports of the design, and they're propagated through the supply network down to the instances in the power domains. In effect, you have to define the entire supply distribution network before you can do any verification. This is one of the ways in which 1.0 kind of assumes that you have the whole design in place, and you can define that global supply distribution network at the point where you want to do verification. In UPF 2.0, we're going to try to postpone that supply network definition by following a more abstract method for defining power states. And in particular, we want to be able to support hierarchical composition. And that doesn't work real well in UPF 1.0 either, for exactly that same reason. If you are always dependent upon the top-level global supply network to do anything, hierarchical composition is kind of limited. You can partition your text, but you have to put the text back together before you can do anything with it. A related issue is this question of what are the supplies for ports of, say, a hard macro? Well, I can't see inside the hard macro and find the power domains in it, but I know there must be some supplies in there. In 1.0, we don't have the ability to model that. So there's additional capability in 2.0 to talk about what the driving and receiving supplies are for ports of a hard macro, even if you can't find that information in the design because it's not visible to you. There are some differences in the way we model domain boundaries. I'll get into that as we get there. And last but not least is we now have the ability to define control logic in UPF. This is a significant improvement because now you don't have to have thought ahead and put all the control signals in the design. We're going to talk about supply sets, which is the key new capability in UPF 2.0, and how that affects power domains, power states, this new concept of sim states, and also how it affects strategies. Supply sets are the main thing that is updating a lot of capabilities in UPF 2.0. We'll also talk a little bit about attributes and control logic. In 2.0, one of the major goals was to support not just the question of what's on and off in your design, but how do you organize the process of developing a low-power design, which involves many teams, many people, over time, IP coming from different places. The whole process is quite complex. And you want to be able to partition the information and express it in UPF in a way that allows you to have information coming from different places, information composed well as you need to integrate in order to support the verification process and the implementation process. There's a lot of issues there that are not really addressed in 1.0. This includes hierarchical composition. We want to be able to use the same techniques we use with IP-based design in the design side to use with the UPF power intent specification. We want more abstract modeling because that will simplify some of these specifications and make it easier to deal with them. Incremental specification. Why? Because we're actually getting the information from different places. The IP comes from one place, the system is developed somewhere else. There's information that has to be combined from the two places. And often some information is built upon other information that came earlier. And so there's a need for incremental development of the specification. We also need more fine-grained control. The concepts in UPF 1.0 were a little bit coarse, and in 2.0, there's been an attempt to refine them and make them higher fidelity with respect to what's actually going on in the hardware. So the approaches that have been developed in 2.0 to address these are, first of all, supply network abstraction. This is the concept of supply sets that I mentioned earlier, which I'll talk about in just a minute, and including the use of supply sets to specify the attributes of ports and IP blocks, especially hard macros in particular, to kind of round out and fill out the concept of the supplies that are used in the design. New power state definitions based on add power state and the idea of sim states, which allows us to specify what the behavioral impact of the different power states is going to be and use that in simulation as well as in reasoning just generally about the behavior. Command refinement approaches this incremental specification problem with a -update option, which allows you now to layer information by extending a command with more information. And there are some other new features that we'll cover briefly, some strategy extensions I mentioned earlier, and the control logic support. So here's back to my example from before. We've got a file called sub.upf, which contains UPF for the sub model at the top. And it's going to create a power domain for sub and everything underneath of it, as before. But then for instance P1 of type proc1, instead we're going to load a UPF file for that one. So we go off to that context and we load this file, which has been written for that proc1 module. Do the set design top to know where we are and create some more power domains. So now we're going to create power domains inside of the power domain that was structured before. And you've seen this before. This is just carving out lower level power domains out of what was already built. And then we're going to go back up and do a load UPF for proc2.upf, do the same thing on the other side. So pretty much the same thing, we end up with multiple power domains carved out. This is hierarchical partitioning of the file using the load UPF command. But this isn't sufficient for hierarchical composition of UPF because it only works when I have everything done already. What happens if I only have this subblock, proc1, and I don't know that it's going to be used in the sub system or in some other system? How do I describe the power intent for this block in such a way that it can be reused in lots of different contexts without my knowing what it's going to be used in? The fundamental issue, again, is that in order to verify this at all, I have to build a supply network. Well, the supply network isn't here. It's in whatever system it's going to be used in. And so we need a new idea about how to model the power states of the system based on a more abstract model of the supply network that can be applied to an IP block like this one. So here's a supply set. A supply set is just a group of supply nets. And you can think of it as the bundle of wires that you're going to connect as opposed to individual wires. So it's kind of like an extension cord. It's got power, ground, and maybe neutral or something. In fact, in UPF, there are 6 standard supplies that are part of a supply set: power, ground, N-well, P-well, deep N-well, deep P-well. And power and ground are always present. You always need at least those two, but you can have some of the others depending upon what you're going to do ultimately with the transistors that are in the components in your power domains. What connections do you need in your implementation technology to make these transistors behave in the ways that you want them to? So supply set allows you to abstract all of that and just say, I've got one thing, it's got all the wires I need, I'm not going to worry about which ones I need yet, but they're all here, and now I can plug an abstract cable in instead of dithering with all the wires. Besides being electrically complete, both power and ground, it has a number of benefits. First of all, we can predefine some of these things. When you create a power domain, there's always going to be a predefined primary supply, which means that you've already got the connections necessary for the power and ground and anything else you need. You can also add user-defined supplies. Here, this supply backup is a user-defined supply in addition to the predefined supply. And you can create supply sets that you want to use as global supply sets that can be then connected to other things. It's like creating a cable that you can plug into different sockets. Finally, we can use these supply sets in a number of ways, such as specifying the supplies for strategies. You're going to see that we'll use them for filters as well in specifying strategies. And in a number of other places, these supply sets ended up being very, very useful. For example, here we are creating This is, again, our proc1 module with the two subdomains defined in it. And this is an IP block at this point. We don't know what the system is that it's going into. But we can say that it has a couple of supply sets as inputs. And these are called primary and memory. I've designated them as P and M over here. Create power domain dash supply is what now adds those things. And if you don't recall the color code, the purple is the extension for 2.0, and the blue part is what was already there in 1.0. I can create a supply for power domain PDMEM when I create it as well. And I'm showing supply primary. This is actually default and predefined, so you don't actually have to say this, but I've shown it explicitly just to make the point. I can associate this supply set up here with that one, which is equivalent to just plugging in the supply set into that socket. Now all the power, ground, NWEL, etc. nets are implicitly plugged into the corresponding power, ground, NWEL, etc. nets of the other supply set. And when I make the connection, I can say connect supply set pdproc.primary. I can now connect them to instances in the power domain based on the PG type information associated with pins in that block. Now this is what I would do if I had a hard macro or a collection of hard macros that had PG type pins that I wanted to connect the supply to. And in fact, it's automatically done anyway for the non-hard macro cells. So you don't even have to say this, it just happens automatically in most cases. And then finally, when I specify that I want a retention register here, I can use retention supply set here, pdproc.memory. So I'm going to route pdproc.memory supply set directly in to power that retention register. So you can see this becomes a little bit simpler. The supply nets are still there, but they're all bundled inside of supply sets. There's fewer commands to write. There's more automation. This is one of the major things that's going on in 2.0. Now, in addition, we can now add power states onto supply sets. Remember, before we put states on ports, we had add port state, and we were defining the states of ports. Here now we're using a new command in 2.0 to add power states on the supply set associated with pdproc, so pdproc.primary. We can say that this supply set is off if the power is off, and it's on if the power is full on at 1.0 volts and the ground is full on at 0.0 volts. This is another place where the level of detail is up to you. I might have said if the power is off or the ground is off, but I chose to make it simpler here. In any case, by putting power states now on supply sets, and I can do one for each of these, I have the same kind of tabular way of thinking about things as before, but they're now based on the supply set and supply set handles associated with the power domains rather than on ports. I also have the ability in UPF 2.0 to talk about the behavior of these various states. In this case, for state off, I've specified SimState corrupt, and for state on, each one of the on states, I've specified SimState normal. This is essentially what you get by default in 1.0. You've just got on and off. When it's on, things operate normally as if the power is on, just like regular HDL simulation. When it's off, things get corrupted because the power is off, things don't function. So we represent that by corrupting the signal values. But in UPF 2.0, you can specify other things. You could say corrupt state on activity. So for example, maybe I should have added a state on 0.6 here, meaning it's on with a very low voltage of 0.6 volts. Maybe that's enough voltage to maintain the state as long as there's no activity in the circuit. And so I could have said SimState corrupt on activity or corrupt state on activity to say this power state will be such that the state of the system will be retained as long as there's no input changes. These are capabilities you didn't have in 1.0, the ability to model those more elaborate sim states. In addition to specifying power states for supply sets, you can also now specify power states for power domains. And in this case, we're adding power state for PDMEM, which is the whole power domain, and defining states up and down based on whether the primary is on or the primary is off. This looks a little simplistic because it's just one for one, but in general, you can define things that are more complex. For example, for pdproc, we can define it to be in a normal state when these two supply sets are in these states and the power domain the memory power domain is up, or in the sleep state when this is off but the memory is up, or in the hibernate state when this is off and the memory is down. So you can see that we can define complex arrangements of power states, and we can make the power state of one thing dependent upon the power state of another. This is what you can't do in UPF 1.0 with power state tables. That's the essential change for 2.0 is power states based on supply sets and power domains as a result. Now there's a couple of related issues. If we have a block like this with a periphery and a core and they have different supply sets, as you can see. So this is the primary supply for the periphery and the memory supply for the core perhaps. Different pins here can have different driving and receiving supplies. In other words, the logic driving one output could be supplied by something that's different from the logic driving another output. In this case, for example, you can see that the logic receiving this input is supply P, and the logic driving this output is supply P. But the logic receiving this input is supply M, and the logic driving this output is supply M. If I can't see inside this box, I don't know what the different supplies are. So it's important to be able to propagate this driving and receiving supply information out to the boundary so that I can find it even if the box is a black box for me. We do that with the set port attributes command for specifying driver and receiver supplies, and they point to supply sets. So if you specify the supply sets in your design, you can connect them to the ports that are involved through these attributes. And this helps in a lot of areas. I'm not going to get into details, but it helps complete the model for what's going on. And again, this is part of the fidelity aspect of 2.0. It allows us to model more precisely what's happening. Now, a lot of hard macros are not defined in terms of UPF. They're defined in, there's a Liberty model somewhere, or in any case, there may be a model that says I have a related supply net rather than a related supply set. In order to be complete, UPF defines how all of those related supply net definitions are aggregated in and turned into anonymous supply sets, so it's consistent with this whole model. And in fact, that then becomes part of the semantics of filters applied to the strategy commands. So here, in fact, are the filters. We have new filters called source and sink in UPF 2.0. This allows me to say, in this case, put an isolation cell on any port where that port is driven by logic powered by pdproc.primary. In other words, logic in the pdproc subdomain. Similarly, I can say put isolation on any port of pdmem that is received by logic powered by pdproc.primary. And then I can also handle the case where I've got a path that goes through a domain and then comes back into this domain. For example, if I have a signal that goes from M1 to proc1 into M2, but there's no logic in here, I don't really want isolation on it because it's just coming back to the same power domain. So there's a diff supply only option as well, which says look at the supplies, the driving and receiving supplies, and only if the driving and receiving supplies are different should we put isolation in here. So these are some of the ways in which supply sets have affected some of the other commands in order to give us more flexibility and make us able to model things more precisely. Last thing, creating logic ports and nets in order to provide control. You can create a logic port, you can create a logic net. This is very much like supply nets, and you can connect a logic port to a logic net. You can then also use that port within, say, a set isolation command without having to have it predefined inside the HDL. Now, in the earlier discussion, we talked about isolating at boundaries, and we said that we're going to isolate at the boundary where the port is interfaced with something above it. We call that the upper boundary now because while UPF only defined the upper boundary of each power domain, UPF 1.0, in UPF 2.0, we are now talking about both an upper and a lower boundary. So it's now possible to talk about isolating a power domain without having to go find another power domain that is underneath of it and isolating there also. You can just talk about this power domain and it's dealing with both sides. A last couple of comments. In 1.0, we had two places where there were two commands that were necessary, set retention and set retention control, and set isolation and set isolation control. For example, set retention came in those two places. This was kind of an arbitrary division between the aspects of retention specification. And in fact, this is now gone in 2.1. And in 2.0, we have this ability to update a command instead. So instead of preordaining that there are certain options you specify on set retention and certain options you specify on set retention control, we now say, here are all the options. There's a minimum set you have to specify every time, but you can update it and add more options as you go. And this gives us much more flexibility and the ability to incrementally develop the specification as we get more information from different places. In fact, one of the new capabilities is the ability to specify instances that have been inserted into the design to implement part of the UPF. And it's a typical use of model to do that with dash update because you're now into the implementation phase and you're adding more information to the command that was used to drive implementation, but now you're documenting what it did. This incremental development spills over into the methodology discussion. So on the specification side, the general approach is to define power domains and the supply sets that are powering those domains, talk about the power states of those domains, and do verification based on that model. And then when you get to implementation, you can worry about defining supply ports and switches and nets and the whole distribution network and connecting them up to the supply sets that are involved in the particular power domains. Let me just wrap up here. So we've talked about supply sets and the various commands that are used to create them, connect them, etc. We've talked about power states, which now are defined on supply sets on power domains. I didn't talk about describe state transition, by the way. There is a command that allows you to say, of all the power states that have been defined, it's legal to go from this power state to that one, but it's not legal to go from this power state to that one. So that addresses the concern about sequencing. We talked about sim states. We've talked about strategies and the effect of supply sets on strategies. The use of supply sets in attributes, and a little bit about the power domain lower boundary. I didn't mention create composite domain, but there is a way to compose two domains into a larger domain. I think there's an example of that later. We talked about control logic, and then there's some other stuff. We talked about load UPF, but not load UPF protected, minor issue. Some other things that we haven't talked about.
I'm Phil Wang. I'm from Cadence. I'm Technical Marketing Director for Low Power Mixed Signal Solutions. I always care about methodology. You know, low power designs, format is one thing. The single format, and many people can write it different ways, create a lot of problems for users and vendors. So the methodology is the way to bring people together. If you look at successful refinement, this is a very subtle and neat concept you need to capture. So from IP creation, IP configuration, IP implementation, we're expecting more and more refinement on the power intent. And on this direction, we call it incremental specification. The IP guys created the power intent. They may not care about what's the library cell you want to use, but they care about where to put isolation, what's the value, things like that. And once you go to the configuration stage, which means that the constraints you provide at the IP creation stage itself cannot drive the actual verification and the implementation. You need more information. At this stage, not only you need to know the constraints like isolation values, you also need to know the control signals. That's what we call about configuration stage. And by this stage, we use a common term called the golden power intent or golden source, which should be the same intent you want to design, verify, and implement. Then go to the implementation stage. This is the whole complete flow from RTL to sign off. Then people all know that during different stage, you may add additional information. For example, which library cell to use, exactly which is the power and ground net you want to hook up to your power intent. And during the stage, there will be changes, but there's also want to make sure you keep the original golden power intent so that you can implement to what you have already verified. That's a very important key thing to remember from the user perspective to design a flow or methodology using the UPF-based low-power design flow. And we call this incremental implementation of the power spec. I will give you some examples to cover each of the successful refinement. This is an example to show that we use multiple commands to address a power intent. Here, for example, you specify constraints that an attribute, say what's the value and where to put isolation. Now, look at here. There's no information about what's the control signal. There's no information about what's the library cell to use for isolation because we are at the constraint specification stage. And then at the next stage, using the configuration, you can use the isolation strategy command to specify the detailed information about control signal and what's the sense and the location. You need to specify value here. With this information now, if you have a verification tool, you can verify your intent here, how it matches up with your implementation rule or instructions. And finally, you can use another command like the user interface cell to specify the library commands, what library cell to use. So this kind of shows that the incremental specification and refinement using multiple commands. You can also use the same command with the new concept inside the UPF 2.0, the dash update. For example, here at RTO abstract, it just says specify the supply set and the power state. Now at this stage, for RTO design and verification, you don't need to specify what's the exact power and ground net for the supply set and what's the exact voltages for the state of the supply set. Go to the implementation stage, you can use the update option to specify, hey, for this supply set, this is my power function is VDD, my ground function is VSS. At this stage, the power function actually refers to the power net, which is VDD. Ground function refers to the ground net, which is VSS. Similarly, for the power state, you can specify for this state what's the voltage value for the power net and voltage value for the ground net. I specifically created an example to show the ground is not to 0. This is really people can use for biasing, like source biasing, to define kind of a sim state that change on activity or change switching. So let's switch the gear to hierarchical specification. That's also a very practical and important aspect when you use the power format in your flow. We will cover two parts very quickly, soft IP and hard IP. Hard IP is kind of the hard block, like modeled by the Verilog for RTO verification or by library cell when you go down to the implementation. We'll use some examples to cover a lot of details we don't have time to cover. So hopefully you will get more information from John and Sushma's presentation when they actually using an actual design example to cover those two subjects. So here we more talk about the coding guidelines, methodologies. The coding guidelines for soft IP, there's many small items, but I want to emphasize on two things. One thing is that one file per soft IP, which should include all the power intent you want to describe for the IP, and also you want to define the interface of supply sets and logical ports. So I will use the example to show what the exact mean by the interface, supplies, and the logic. So if you look at these designs, I have three blocks. The block shows a little bit shaded as hard IP. I will do a little bit later on. Let's focus on the two blocks of the so-called soft IP. One part is the whole design in one power domain. One part is the blue in another power domain. Let's look at the examples of what we can do to create this soft IP power intent. The first part, you define the logic interface. As Eric mentioned, using the UPF 2.0, you can define new logical control ports for isolation or state retention. Those ports don't have to be in the RTO. So that's the way you're going to create it. You define this port, even though this port name called ISO_enable is not in the RTO, you can do that. Then you can define the interface. This really basically is what we call this top level power domain. I include scope to say everything below this belongs to this power domain. You can define your interface supply using the dash supply option for the power domain for the top level power domain. So this is actually in the example that Eric showed, this put here with more context. And essentially this so-called interface supplies basically to model all the external supplies coming from outside the world into your IP. At your IP level, you don't actually care exactly what's the supplies coming to my IP, but you definitely know that at the architecture level, my IP need two power supplies. And that's the supplies you want to define here. And here is all abstract level. You don't have to specify all the detailed information. With those interface established, then you can define your power state for all the supply handles. At this point, you don't even have the detailed power VDD or VSS. But what you have is supply set or supply set handles. You can define power state. You can define the global system state on the top level power domain. Then you can define some kind of isolation strategy. Okay, that is almost kind of the full power intent. Interface, logic interface, power interface, the states of the supply handles level as well as the system level, and then some strategies. This pretty much is your soft IP level's power intent. Once you have this IP power intent, then how you hook up, right? That's the key thing. UPF 2.0 gives you a very systematic approach to link or to combine or instantiate it or integrate your soft IP into SoC designs. Several things, key things to remember. Load UPF-scope. This is the command, be able to load your IP level UPF to SoC level. Eric talked about that. Then, again, this is also talk about associate supply set to link the interface supply with the top level SoC level supplies, and use the connect logic net command to link the logic interface to the SoC level. So very quickly here shows that at SoC level UPF, you load this block level UPF to this scope and use the associated supply set associated the lower scope supply set handle, which we define as interface, to the top level supply set or supply set handle. You can connect the logical net similarly using the connect logical net command. Very systematic way to create the IP and instantiate or integrate your IP at the SoC level. So this is for the soft IP. What about for hard IP? We can do it in a very similar way. A hard IP, currently people using UPF 1.0, typically using Liberty. That's perfectly fine. However, we want to show that using the UPF 2.0, there's a better methodology to address, you can describe more complicated hard IP with power management features. And again, the coding guidelines is still the same. 1.5 per hard IP, and you want to include all the power intent inside of that. So two supplies coming in, there's one internal supply, and you have some logic related to this external supply VDDA, some logic related to the VDDB, and some logic related to the internal switchboard supply. And it also has some internal isolation. So this is your complex hard IP. This is very similar to the soft IP I just showed in the previous slide. Actually, the methodology is kind of recommended is deliberately make to be similar so that you can reuse your IPs. And here, still, you define your interface supplies. In here, you have two external. You define SSAH, SSBH as the external. So this is your interface supply. And typically for the hard IP, you probably has all the pins on the hard IP, so you don't need the interface for logic. But in some cases, you still need it. You can then use the previous example to do that. Here, I'm only showing the interface for power supplies. And then you can, now, because it's a hard IP, already have the power and ground net over there, you can immediately link your interface supply with your hard IP's power and ground pins. Then you can also use the port attributes to define receiver supply and the driver supply to link your pins with the supply sets or interface supplies you defined for this power domain. And finally, you can define the power state on the supply set handles as well as on the system for this hard IP itself. So there are several things that you cannot do with Liberty, specifically is the power state. It's allow you to specify your power states for your hard IP, be able to help you to do the SoC level integration and the checking. Now with the hard IP specification, how we're going to do the integration? Again, very similar to the soft IP, load the UPF-scope, link it to the specific block, and then use the associate supply set to link the interface supply for the high IP and SoC level. So in here, we show that here is the hard IP as before. Then what the UPF code looks like is even simpler in this case. Load UPF for this UPF file -scope on this cell, and then you do the associate supply set of the IP level interface supply with the top level supply set or supply set handles. Again, very systematic way in using UPF 2.0 to define hard IP intent and the linked hard IP at the SoC level to do the integration.
I thought to add some detail to what Cheese and Eric have been talking about earlier, we'd go through an example of using UPF for IP design. Because a real-world example might be a little bit complicated, I've made a Cortex-A series MP core example. It's a sort of generic, simplified example that is representative of modern ARM processors such as the Cortex-A7, Cortex-A15. It's a symmetric multi-core cluster that can be configured for 1 to 4 CPUs and also has L2 cache at the top level. Each CPU has 2 power domains. Essentially, there's one power domain for the floating point unit and the SIMD accelerator, and then everything else is in the other power domain. That would be the integer CPU, the L1 cache, debug, trace, etc. At the cluster level, there are 3 power domains. There is a power domain for the L2 cache RAM instances. There is a power domain for the debug and trace blocks, and then essentially everything else, the cache control circuitry. So this is a block diagram I lifted out of one of our technical reference manuals. It's a little bit difficult to see what's going on in black and white there, so I've overlaid it with some color to show those power domains that we were talking about. And specifically, one thing I wanted to highlight was the location of these clamp cells. The clamp cells in this diagram are shown as appearing immediately after every power domain crossing. But as Eric was mentioning earlier, if your library supports it and you have dual rail isolation cells in your library, you can actually implement the clamp cells in with the logic hierarchy. So that clamp cell in blue in the sea of purple there is showing the fact that you would need dual rail isolation cells in order to build a block that isolates its own outputs. So whilst we're talking about the relationship between logic hierarchy and power domain hierarchy, I just thought I would highlight a gotcha that has tripped up some people with UPF1, and it can also trip you up in UPF2, but there are ways to avoid it. And it's specifically to do with a multi-element power domain. So if you have a simple hierarchy like this, where you've got 3 modules, A, B, C, in the top, and you want to create a power domain red out of modules A and B, you might simply go create power domain red dash elements A and B. And then you might apply an isolation strategy to that power domain red. And then you might be surprised to find that you get an isolation cell between any nets that leave A and enter B. And that's because most implementation engineers are used to design compiler where you group A and B together and it becomes like a new level of hierarchy. But the way UPF works is the power domain red's boundary is the aggregation of the boundary of module A and module B. So the fact that the net leaves A means it leaves power domain red. And if you think about it from a Verilog perspective, the wire that connects A and B exists in module top. And so that's why you get this somewhat unexpected isolation. So a different way of approaching this to avoid that would be just start at the top. Put all of the elements into your power domain red, and then, for example, call out blue a separate element where the more specific definition overrides the more generic. And now module top belongs to red, and you don't get the problem. In UPF2, you'd be better off doing this with the commands that Eric was talking about a few minutes ago, diff supply net only. This would be an example where if you said set isolation diff supply net only, you wouldn't get the isolation between A and B, or you could use source and sink filtering to avoid it. That simple workaround doesn't work when you have a more complicated hierarchy like that, which is why you'd resort to diff supply only. So diff supply only would work from B to E as well. A far better approach in designing IP is to try and align your logic hierarchy with your power domain hierarchy, and then that problem just goes away. So getting back to the Cortex-MP core example, we looked at the power domains that exist. Here's a tabular representation of the power states that are allowed for those power domains. And I just wanted to highlight that you can define things when you're writing in a natural language specification or just putting a table down that, for example, when we're in the CPU retention, we don't actually care whether the FPU is in retention or off, it just shouldn't be on. And so you can cover a lot of state space with these kind of simple statements. And the good thing about add power state in UPF2 is it also allows you to do this a sort of painting of the state space, so you don't need to build an exhaustive table like you did in UPF1. So add power state is a lot more efficient in UPF2 in describing your power state. I'm going to just very quickly repeat what Chi said about successive refinement, because I want to draw up a reference to the interfaces here. So an IP provider creates the RTL and then creates some UPF that constrains the subsequent configuration of that RTL and limits the scope that the licensee can configure the RTL into. And then the licensee will create a specific configuration of that low power intent and invest heavily in the validation of it. And the nice thing about the successive refinement is it allows you to, when you go on to the implementation, you can then add the color of the implementation without having to repeat all of your verification. So you're preserving your verification equity that you've invested in the golden reference. That first brick wall in the diagram is what an IP provider provides. And really, essentially, it just breaks down into 4 things. It's not very much. And the four things are, number one, the atomic power domains that exist in the domain. I call them atomic because they cannot be subdivided. They're the finest grain resolution of the power domains in your design. You could merge them together when you do your implementation or ignore them altogether, but you're not allowed to go and cut one in half. And then for each of these power domains, you need to specify the state that needs to be retained should you shut it down. And this needs to be done in a way without predicating how that state's retained. So you don't want to get into the details of whether it's a single pin retention strategy or a two pin retention strategy. Number three is the signals on the power domain that need isolating should you shut it down. And again, we don't want to get involved with saying how those signals are isolated. We just want to provide the constraint that they must be isolated. Some signals will have a semantic where it's important it's isolated in active. Some signals have no semantic, and you just say it needs isolation and you don't really care whether it's high or low. And then lastly, and perhaps the most important one, is the constraint of the legal power states of the power domains that we've defined and the legal transitions between those power states. And here, you want to do that without getting involved in absolute voltages. In UPF1, it wasn't possible to do without talking about absolute voltages. So what does that look like? So let's have a look what that might look like for a CPU. And here I'm using the term CPU to mean one CPU in a multi-CPU cluster. So I use the term cluster for the entire thing and CPU for the processing unit inside the cluster. So as I was mentioning earlier, there are two power domains. So in UPF, you'd say, create a power domain CPU and put everything in it. Eric pointed out to me a little earlier today that this is actually a UPF 2.1 way of doing it. Dash elements dot is bang up-to-date syntax. If you were doing it in UPF 2.0 today, it probably should say include scope, which is, I think, what you were using in your examples, Eric. So once you put everything in create PD CPU, we then pull out the floating point unit. And I've not bothered to give instance names. Excuse me, I've just used a variable here for clarity. So pull out all of the elements that comprise the floating point unit. Then I wanted to constrain the retention, taking a simple approach here and saying everything or nothing must be retained. So that means don't try and do selective retention. This set retention elements list creates essentially an atomic list of state that must be retained or not altogether. And then here are my isolation requirements that I'm putting on for the CPU. So essentially I'm saying all outputs must be clamped low, and then using the more specific overrides, the more generic concept in UPF, I go ahead and override a select few of them that need to be clamped high. In terms of the power state, we're going to create the power state for the domain FPU and the domain CPU, and the power state's going to be defined in terms of the supply sets. So the domain FPU has supply sets, a primary supply set and a retention supply set. When they're both on, we're in state run. When they're both off, we're in state off. But if the primary is off and the retention is on, we're in state retention. And that's essentially what's saying here in this power state commands. And now we're going to move on to define the power state for the CPU in terms of its supply sets, but also in terms of the state of PDFPU. So now we have a primary and a retention supply set for the CPU, same kind of thing as we got for the FPU, but we can also add in here the state of the FPU that contributes to the state of the CPU. So now we have constraints on the state of the whole CPU block. And there's that little trick by saying the FPU can be in any state except run. So moving up a level, this is what this little moniker in the corner is supposed to indicate. We're now up at the cluster level. I've only done the 2 CPU cluster because the difference between 2 and 4 didn't help with the examples. So here we're creating, again, atomic power domains. We're going to put everything into the cluster domain and then call out the L2 RAM and the debug like we did with the FPU for the core. And again, the retention strategy, we're going to say all or nothing. And here are the isolation requirements, again, very similar to the core. We're going to ask for everything to be clamped low except for a few specific signals that are being clamped high. The cluster constraints, again, like we did with the CPU, we're going to define the power state of the L2 RAM in terms of its supply sets, define the state of the debug domain in terms of its supply sets, and then moving on, we will define the state of the whole cluster in terms of the state of its constituent power domains and its supply sets. So we've got the cluster's primary supply, There's no retention at the cluster level. And then the states of the L2 RAM, the debug, and the CPUs. So here you can say the cluster is considered to be in mode run when everything is on, and we don't care what the debug is doing. Conversely, we're considered to be in debug when the debug is on and we don't particularly care what all of the other modes are. And one of the nice things about add power state is with the refinement and update, you can go and add further resolution later to these power state tables if it became important for during implementation to differentiate between different types of run. You could go and break that run state in half and add, say, a turbo state, so you can refine as you go through the implementation, adding more space as required. So we now have UPF constraints to go along with the RTL, and this is essentially what an IP provider would deliver. So now we're in a position to begin considering configuring those constraints for our application. So at this point you have a choice. You could either do flat configuration from the top or a hierarchical configuration more from the bottom up. Now clearly if you do it flat from the top, it's probably a little simpler and more straightforward. Everything is within your scope, so as you create your, say for example here, I'm creating some isolation and some power switches, I can just kind of reach down into the hierarchy and reference the nodes that I want to isolate, the supplies that I want to switch, and I can also reference the appropriate outputs of my power management unit. However, there are other reasons why you might want to do a bottom-up hierarchical implementation, perhaps due to limitations of your physical implementation tools, capacity management or concurrent engineering. There are a number of reasons why that decision may already be predicated as being a bottom-up implementation flow. So in the case of a Cortex A-series core, it's quite likely you're going to implement the CPU before integrating it into the cluster. So I thought for the rest of this example, I'd go through the hierarchical approach. In order to configure hierarchically, then you need to configure your IP out of context. And in order to do that, you don't have access to the output pins of your power management unit. So when you're going to insert your isolation or insert your switches, you've got nothing to wire it up to. So this is why we needed to add to UPF2 the create logic port, create logic net, so that we could add this to the RTL without having to modify the RTL. So now we can create the ports that we want to use to add in the switches and the isolation like we did in the top-down. And then we will go and put that IP in the context. So we change our scope up to the next level up, load in the UPF, and in fact I'm using the same UPF here for the two different scopes. And then again create more ports, connect them up, and then eventually wire those up to your power management unit at the top level. So that's how you'd have to do it block hierarchically bottom up, a little bit more complicated. So let's look at that specifically for my Cortex A-series MP core. In order to do the CPU configuration, I decided to compose the CPU and FPU domains together, partly because it made the example simpler, but partly because I also wanted to show composed domain. So here we're creating a composite domain, and we're going to call it my CPU, and it comprises of CPU and FPU. And I'm going to need to create the control ports in order to hook up the isolation and the power switch for that. And I'm going to need to fulfill my isolation requirements with two isolation strategies, one to clamp the most outputs low and one to clamp the odd CPU clamp list high. Now we're coming to configure CPU supply set state and power domain state. So we need to update the supply set state with supply expressions, and we need to update the power domain state with logic expressions. So for example, here it's showing that the CPU will be in mode run when N power up CPU is low. It's an active low switch. We've got PMOS switches, header switches. And I've chosen here to, in configuration, make retention illegal for the CPU. We don't need it, so we're going to make it, update it to be an illegal state. And then finally, I'm going to add some state to my new my CPU domain, and I'm simply going to make it run when the CPU is in run and the FPU is in run, and off when the CPU is off and the FPU is off. So a very simple configuration. Then we move up to the cluster level. At the cluster level, I've got to create all of these ports to control the various power domains, isolation and power switching. And also, as we were talking before, I've got to create the CPU power control ports and then I've got to connect up the CPU power control ports. So that's sort of like connecting the isolation and power controls from here up to the power top level domain there. So create a retention strategy for the L2 RAM and create the appropriate isolation strategies here for the various isolation requirements on the power domains. Again, clamping most of the outputs low and the exceptions high. Now, at the cluster level, much like we did at CPU level, we're going to need to update the supply state with supply expressions and update the domain state with logic expressions. So at this point, we now have our golden source. This is simulatable and verifiable. It's not implementation specific, but it is application specific. So you now can go and invest in your verification without worrying about, as Eric was saying, what the name of the power supply is, or even worrying about whether you have to repeat all your verification once the power supply architecture has been chosen, or indeed named. So let's now move on to the implementation of our little example. So in order to implement it, we're now going to have to name our supply set. So we're going to create some supply nets. And I've chosen to create supply net VDD and a VDD CPU and a VSS. And then I'm going to update the supply sets. And I'm going to say that the function power is hooked up to CPU for the primary supply. And the function power is hooked up to VDD for the isolation supply. And this is the technology-specific bit where we're mapping the various isolation strategies to specific isolation cells if the EDA tools can't infer them for themselves. And then finally, we need to create a switch that actually fulfills the power state that we've described in the configuration. So this switch that we're creating here, it drives VDD CPU, switch output, from VDD switch input. This is the switch control, this is the power up, and it's on when power up is low. Again, so this is a PMOS header switch. I won't go through the details of implementing the cluster. It's very similar. There's just more of it because we've got more power domains, more isolation cells to map, and then more switches to implement to switch the power domains. And then at that point, we've got a full description of a technology-specific implementation of an application-specific configuration of the constraints that the IP provider provided. And you could go ahead with the right-hand side of that diagram that shows all of the normal implementation down to a fully PG-connected place and routed cell. So most likely, this will be handed off as a hard macro up to the SOC level. And the advantage of handing off as a hard macro is that you no need to re-verify the implementation. In fact, all you need to do is just re-verify its integration into the SOC. And in order to do that, you need a power-aware simulation model that does all of the corruption and retention behaviors that you would expect during shutdown. And it probably has some assertions that make sure that you're controlling the power domains in the right way and sequencing it in the right way. You'll also need a Liberty model with full PG syntax for the physical tools. And that should have the related power pin information in there and power down function, etc. And then in UPF1, we also used to have to do this trick where we created kind of macro level UPF that was descriptive and not directive. And that's what this little picture here is showing. If you had a macro with internal switching, this power supply here, as Eric was saying earlier, it's not obvious how you describe that this logic is being driven by that power supply. And in Liberty, you do related power pin. And in UPF2, you do set port attributes -model. But in UPF1, we used to have to create a kind of shadow switch that was outside the hard macro, but was describing what was inside it. So you can do it in UPF2 with set port attribute, but coming in UPF 2.1 is even better support for hard macro cell modeling. We now have a more structured approach with begin power model, end power model, and apply power model. Alternatively, you could just simply use the RTL and UPF that you use to implement your block and hand that over with your core to the SOC integrator.
We saw the different concepts involved with UPF. We looked at hierarchical composition, and we looked at how to create a hard IP. So we're going to put all this thing together, and we're going to try to build a system level or an SoC. This talk's going to be broken into 3 sections. So we're just going to go over the problem description. Then we'll take specific implementation examples. So this would be full-blown implementation of blocks. And we're going to take two different examples. One is a hard IP block with 2 domains, and then we're going to take I/O paths, which is something which is specific to the top level. It's not typically seen inside IPs. And finally, we're going to talk about SoC integration, what are the useful tips, general best practices, and also talk briefly about verification. So a typical SoC consists of hard IPs, and John just mentioned how we could build a hard IP with an ARM core. It also has a lot of soft IPs, and soft IPs are typically HDL, which we directly integrate at the top level. In addition, you could have plenty of analog or mixed signal macros, which you get as simulation models. And then, of course, you have all these I/O pads because you have to interact outside the chips. And I/O pads are interesting because they typically have multiple power pins. So we now get to see the whole gamut of all different types of implementations at the top level. So what are the main challenges? The first problem is we just have too many power supplies now because you're taking into account all these different 1.8 volt, 3.3 volt, 2.3 volt supplies in addition to all the digital supplies. So we just have a number of power supplies and their connections. Also, just at an IP level, we saw so many different power states. Now, if you translate that into a SoC, you just have an explosion in the number of system-level power states. And then it also becomes a problem of how do you organize, how do you modularize, how do you sort out your UPF. And just like we have problems with HDL, you have multiple files and you partition it into different files, we deal with the same sort of database management problems with UPF. And finally, when you want to talk about strategies, where to put isolation, where to put level shifters, and going into the details of implementation, so that question shows up at the top level. So what we're going to do first is look at the implementation of a block. And we're going to look at 2 different implementations and then talk about SoC integration. The way RTL designers are used to like a timing diagram or like a functional spec, we should have a similar diagram which is called a power implementation spec. So this diagram kind of illustrates how to implement a power domain. And we could use this as a starting point for writing UPF. What you see here is a block, and it's color-coded. So I'm going to start off with domain definitions. So we have 2 different colors on this block. One's pink and one's blue. And we're going to start off with a switched power domain, which happens to be the pink one. And then we're going to create another domain, which is an always-on, which I call always-on domain. It's a blue block, and that's color-coded in blue. And the colors help us, kind of understand the different domains better. The next thing we're going to do is we're going to add supply ports into this block. And by default, all supply ports have direction input. But you'll notice, interestingly, on this block, there's a switched port, which we use for observation at the chip level. And that's actually direction output. And that we need to specify explicitly here. Because this switch port is generated by an internal power switch. And we'll see how we can model that switch shortly. So we create the domains, we create the supplies. The next important thing that we need to focus on for an IP especially is the set port attributes. We need to talk about what drives out and what comes in it. We need to model the IOs very carefully. That is also color-coded on this diagram. What you can see is some of the IOs are deep blue, and these are what I call my always-on IOs. Some of the IOs are deep purple, and these purple ports are related to variable power supply. And we'll talk about these supply sets briefly. It's very important for us to model the IOs because it tells us what type of buffering we need to apply for this. And buffering is a typical implementation problem. By default, any buffer that goes into the pink domain would be a regular buffer or a switched buffer. But if you need to buffer it with an always-on supply, we typically have to use a special dual-rail buffer called always-on buffer. So in this particular block, we have 2 cases where we would need to do always-on buffering. And to indicate the need for an always-on buffering, we need to use the set port attributes. Also, to indicate the need for isolation or level shifting, we also have to use set port attributes for IOs. So we've already spoken in detail about supply sets. So what you notice here is different compared to the rest is that you can be more specific and add complete implementation details. Like we did not talk about N-wells before, but depending on implementation, the N-well could be connected to a switch supply or could be connected to an unswitched supply or an AON supply. So with each supply set, you could not only define the power, not only define the ground, but also define the N-well connections. and POL connections and other connections if you have so. So let's continue to talk about supply connections. So create power switch is, as indicated in this diagram, you see a power switch. It's got an input supply and output supply, and it's got two control ports. So you could have one or two control ports, and you have two output ports. You have two acknowledged ports. So as you can see in this example, the first column here refers to the pin name on the library cell. Like VDD here happens to be the pin name on the library cell, and VDD switch happens to be the port that it connects to at the block level. So the right-hand corner refers to all the design level ports, whereas the left-hand corner refers to all the cell level pin names. And you basically make connections between each of your inputs, each of your ACK ports, and define what's the function of that ACK port. In this case, the power on out happens to be a assigned statement of power on in. And you can also define what is the condition for which this switch turns on or off. If you're familiar with UPF 1.0, we had this command called set domain supply net. Well, that is replaced with a command called associate supply set. In UPF 2.0, you can do associate supply set and define the handles. So in our case, we have two domains, a pink domain, a blue domain. The pink domain is switched, the blue domain is on, and we just define it with their respective handles. Now, what happens to the non-default connections? So what are non-default connections? Anything that's not directly covered by a domain definition. In this particular example, we see there is a PLL, and the PLL has a 1.8 volt supply. It has an analog ground. If you do not do anything, by default, this PLL logically belongs to the PD switch domain. So it's going to get connected to the switch supply. It's going to get connected to the regular VSS. So if we need to make an exception, we need to explicitly connect that PLL to the analog power supply. So what we've done here is there's a 1.8 volt supply that's defined. I want to connect that power net to the pin called AVDD1P8, which happens to be a power pin on the PLL, which requires a 1.8 volt supply. And what you also see interesting here is that we use find objects. So there was a question about how to use wildcards. So if you don't know exactly which hierarchy the PLL belongs to, we could use find objects and use a pattern with wildcards and tell that, this is an instance name, and this instance name should match this pattern, and it's a leaf instance indicating that it's a library cell, or it's a leaf cell, it cannot be decomposed further. And you could make this explicit connection to the PLL. Isolation strategies. So in this particular example, we've kind of kept everything self-contained. We want this IP to be self-contained, so the isolation happens inside the IP versus at the top level. So what you see is there's isolation going from the block to the top level. There's isolation going from the switch domain into the AON domain that you see here. We also use diff supply, which John mentioned. It makes handling crossings easier. So we use three sets of commands. The first command to describe where you want to isolate. The next set of command to tell exactly the location where you want to place it and the type of signal you want to use. And the third command, which tells you what specific library cell to pick. You could combine these two into a single command, but basically you have three sets of commands that you could use to completely describe the complete implementation of an isolation cell. And you could do the same thing for the AON domain. In this particular case, we've decided not to use level shifters. And if you want to specify not to use level shifters, you could specify that by using a command called set level shifter. What is the condition for not using level shifter? In this particular case, what we are trying to tell the tools is to ignore putting a level shifter if the voltage difference is less than 0.2 volts. So if the voltage difference is less than 0.2 volts, you want to skip adding a level shifter, and that's achieved by using this command called set level shifter. You define the domain for which you want to set the policy for. You define the sink, which happens to be AON, and you define a dash threshold. So that helps you to skip placing a level shifter, and which tells the implementation tool not to add level shifters if the voltage delta is less than 0.2 volts. The interesting part, supply states. So if we go back to our diagram, we saw four supplies. There's 1.8 volt supply, there's a variable supply, there's a switch supply, and there's a ground. So how are we going to describe that in a power state table? So on your rows, you have the different supplies or supply sets. And on the columns, what we see is we have different states. So we have three different states, nominal, turbo, and off mode. And for each of these states, you could in turn have specific VDD, VSS, and NWEL values, which stand for power, ground, and well. And what I've populated here is specific voltage values. So this is like once you get to a point where you're implementing, you have specific voltage values and you can drive implementation tools with this. So you would just translate this table into following. So when you want to describe supply states, you use supply expression, and John mentioned this as well. So if you have 4 supply sets, you would typically have 4 add power states with supply expressions, and you're going to define all the different conditions, like you define the power being 0.8, ground being 0, and NVEL being 0.8. And what you also notice it happens typically is that some of the supplies are constant. They just don't change. Like your AON supply, there's only one value, it's 0.8, and that's it. It can either be 0.8 or nothing. What you could do in that case is to use dash illegal and say if power is not equal to 0.8 volts, it's illegal. So how does that help? How does it help us to identify illegal states? Well, it helps us when you're trying to build a system level power state. So what we have now here is we took individual supply states and we're trying to build a system level or a domain level power state. So what we have here on the rows is the different domain states, and on the columns you have the different supply sets, and for each supply set we're going to go through each of the supply states. So it's just like how you would create your power state tables in your one auto, but just another way of looking at it. So what you'll notice is even though I have 4 columns, I have just 2 virtual columns in this particular example. And the reason was, in this 1.8 volt column is constant, and the AON column is also constant because this is always at 0.8 volts and this is always at 1.8 volts. And I have defined every other state that's not 0.8 or 1.8 for these 2 supplies as being illegal. And that helps me, reduce the size of this table, and that helps me reduce the number of permutations and combinations I have to make here. So pretty much that reduces my set of combinations to a variable and a switch. So what we have to just do is, now that we have 5 states, you just go over all the 5 combinations here. And this would be your entire IP level domain state. So that's one way to look at it. Now the next example, we're going to look at something that's even more implementation centric, and this is using IO pad connection. What's interesting about a pad? Well, it's pretty simple. You've got power pads and you've got signal pads, and the pads typically have a pad side interface, which is usually a higher voltage, like a 1.8 volt or 1.2 volts interface, and a core side interface, which is usually your digital logic supply voltage. And it's all about managing the connectivity. And sometimes in the past, people would hardwire all this. So in your RTL, in your top level RTL, you would see tons of VDD, VSS, AVDD, VDD 1.8, etc. present in your HDL because these used to be wired up like signals. And that's not really good for implementation because implementation tools really value treating signal and power supplies differently. So how are we going to model something like the IO pad? Same rules. We create supply ports. So instead of creating it at an IP level, now you're going to create this at an SOC level. And your SOC level power ports would be listed in the create supply port definitions. And then you would have to create a supply net. In this case, I've just kept the supply port name and the net name identical, so it's useful. It just maps to a more Verilog concept where if you create a port, there's an implicit net and it has the same name. So this is actually redundant because when you create a port, you get an implicit net in Verilog. So we have a supply net. And what we do is we connect the supply net to the pad. So this is a power pad connection. So what we are doing is we take an external port and connect the net to the pad pin of a power pad. In the next case, the power pad internally generates another supply, which is what is used inside the chip. And that's what we call the core side supplies. So the first step, we just connected all the pad side supplies. Now let's see how we're going to make the core side connections. So what we're going to do now is we're going to take the output of each of these pads and we're going to create 4 more new nets, and that's on the side. And we're going to connect those nets to the output of these pads. So the input of the pad was connected to the primary input. The output of the pad is connected to an internal net, just like you would connect a port mapping and a wire connection to a port. So this is just pretty much wiring up. There's like no abstraction to it at this point. It's just physical wiring. So you would just do a connect supply net and you would connect it to the output side of the pad. And then you're going to connect it up to the power pins of your signal pads. And that's also achieved through connect supply net. So with the simple command connect supply net, you can hook up your entire power pad. So you're going to have supply states associated with that. Here we've taken a very simple example, so I'm going to skip this because we've kind of covered this in the past. We've moved to the third section, which is really building a system-level SoC and what are best practices to follow. So how many UPF files are we supposed to have, and at what level should I create a UPF file? And this question is very similar to how many HDL, how many .v files or .vhd files you would like to have. At what level do you really partition your design? A good rule of thumb is if you have a place and route block. So it's absolutely a must to have a UPF for that if you're trying to implement that block standalone. So you would need a UPF for a place and route block. On the other hand, you could go more granular. So pretty much for every power domain boundary, you could create a UPF. And you could go more granular than that, but you're kind of adding more files, and it just becomes a problem to maintain. So just creating a UPF for a place and route block boundary or a primary power domain boundary is good enough. And what we do in our top level is that once you have your sub-blocks created, we would just load it. And one of the things that we find useful is instead of hard coding a path, because your file, your directory structures could be, you could change them from project to project. So using tickle variables like $env UPF path, you could actually use a system of make files or something and pass the exact directory where you actually stored the file. So that way the file becomes more reusable from project to project. So you create files for your sub-blocks and then load it in your top level. The other question that's typically asked is, should we put isolation cells inside the block or should we put it at the top level? And there are different answers to this depending on the availability of cells. But from an implementation ease standpoint of view, if you have fewer domains, few, it's a subjective word, but it's like 2 to 5 domains, you could pretty much manage everything at the top level. But as you keep scaling your design, and if you have 20, 30, 40 power domains, if you're going to have all the power management cells sitting at top level, from an implementation standpoint, it becomes a little more complex to manage routing, managing, and connecting these power management cells. So it becomes better if you move it inside the block. The block itself becomes self-contained. You can verify the block standalone. It's complete with respect to power management. So it's a trade-off that you have to make depending on the size and complexity of your design. Modularizing a top-level file. Once you start having lots of power domains and you start putting all these power ports and system-level power states, your file is going to grow really large and it's going to become unreadable. Just like you would break up your HDL into more readable chunks, you'd like to partition your UPF file into more readable and easy to understand chunks as well. So what we could do is use a source command. So source is different from load UPF in the sense load UPF is for reading UPF files for a specific scope, and it applies all the UPF semantics while loading it. Source is just like a tickle command. You can just source a file. What it just means is it's just going to take the contents of this file and concatenate it while building the file. So source is just an easy way for us to break a big file into smaller chunks. It really does not make the file hierarchical in any sense. For instance, if I source this file, whatever scope this source command was issued at, that would be the scope at which all the commands in this file would get processed. So it's important to know the difference between source and load UPF. We've already covered I/O modeling, and that's a big issue when you have a huge SoC. One thing to note is that you could make life easier by following some good naming conventions. And what's the advantage of naming conventions is that you could use some pattern matching and make some connections easily by using the find objects command. So just like HDL helps to have naming conventions to make some automatic connections. There's another concept which is a 2.1 feature, which is the new feature. It really helps us to reduce the size of the different combinations you have, and that's the set equivalent. Typically what happens in an SoC, you have tens of supplies, but they actually have the same functional value. They're either connected off-chip or on the package level. So they're electrically the same, except that they appear as different power ports when you have your SoC. And it's really useful to use this command called set equivalent to say, functionally, these guys are all the same. They're electrically at the same potential. And that way, you can reduce the number of supply combinations you have to go through and the number of supply states that you have to specify. But again, this is something that's a new feature, but very useful feature. So again, macros, we've got to watch out for analog macros or any special macros. Because the connections to macros don't happen by default, you've got to watch out for all non-default connections. So if you're reading a .lib for an analog macro, you've got to watch out for the fact that the .lib should actually have the PG pin definitions and related pin power ground definitions. And if you're also dealing with macros which have internal supplies and internally switchable supplies, that may not be apparent when you're trying to hook it up. So that's something that we need to additionally take care of. So this is just an example to show how you could make a non-default connection for handling macros. So in summary, based on all these concepts, how would your top-level UPF look like? So we start off with some blocks. So you have a core, pads, you just load the UPF. Then, depending on what type of mode you want to implement in, you could have additional tickle variables that you would pass. In this case, I'm using an environment variable called higher mode. So if hierarchical mode is true, I load the UPF for a hard block. And why is this important? So for instance, if you were to do a synthesis or if you want to do a top-level implementation, you may not need to load the UPF of the ARM block, maybe because you have a .lib, in which case you don't need to load the UPF. But if you were to do simulation and you have the HDL and UPF of that ARM IP, I'd rather like to load the UPF with the HDL and simulate it as a white box. So you could add additional environment variables to put in some conditions inside your UPF whether or not you want to load some files. You would create your power domains, and then you would break down the file into different logical units and then load different components of the file. Just an example of how the top-level file could look. So individually, each one of these files could be large, but it just makes the top level a little more organized, and it helps you visualize how to build it. The most interesting part is top-level supplies. You've got lots of power supplies, and you have to deal with different voltage combinations, and your power state table is going to explode. So what we're going to look at is a simplified example with just 4 variable supplies, some I/O supplies, which are all constant at 1.8 volts, and 1 AON supply. And how to create a power state table we've already looked at. Just translate this table into add power state. Note that since these are all supply sets, right now we're dealing with supply expressions. Now, how do we start writing a system-level power state? The brute force way is you just start listing all possible combinations. And then you go crazy because there's just so many of them. So how do you simplify this? So how do we write truth tables in general? You write truth tables, and then we mark certain states as don't care. And that leads to a simplification of the truth table. So we're going to simplify this truth table now to something that looks like this. So you've taken the top level, which is an exhaustive set of all combinations, and you've reduced that to logical expressions that looks like the following. And what you would do is once you build a truth table, which is a more simplified version of your exhaustive list, you're going to take that truth table and then try to translate that into an add power state. So for instance, what we have here is the I/O supply and the AON supply are always on at a constant voltage. So we are probably going to declare the other states as illegal so that we don't have to worry about these. So pretty much the supply sets that are of interest are these 4 because they seem to have some combinations. On top of it, this variable 3 supply set also seems to be pretty much constant. So you could declare anything other than this or this to be illegal and therefore reduce the number of combinations you need to supply. So pretty much the contention is between var1, var2, and var4, which could have different combinations. And that's how you simplify your system-level power state and you get to a more reasonable, readable kind of power state table. We spoke about power states. What about transitions? How do we go from one state to another? Is it legal to go from all states? And for this, again, you need to build like a system-level state diagram or state bubble. So you tell what are valid and what are invalid combinations. So it's always easier to start off with the invalid combinations first. You just rule out that anything going from this state to this state is illegal. And you do that with a command called describe state transition. So what we've done here is we have a state transition called I1, which goes from all off to all on. And we've declared that from all off to all on as illegal. So we had defined all these states in the previous state table, and we're now defining state transitions. So similarly, we're going to define all the different illegal combinations. And that helps us eliminate a major chunk of our combinations that we are not interested to verify. Or we want to verify and make sure that those combinations are not entered. Or if they enter, they're going to cause illegal results. And once you've identified your illegal combinations, you are going to similarly start building legal combinations. For instance, P1, where you could go from all on to either var1 off or var2 off. So this is a legal transition called P1, and you capture it through this particular state arm. And similarly, you could build it for all different system states. And this is very important to make sure you get correct coverage, minimizing the scope of what you need to check for. Finally, a quick note on how to build an SoC bench. So we've already seen that you could use a set design top to pinpoint the hierarchy that you want to focus on. And then you can load the UPF, and this happens to be a full chip UPF. I've taken the example of a Verilog test bench, but whatever test bench you have, the important thing is you would need to import some of the UPF packages, which give you functions like supply on and supply off. And so what you've noticed is in the initial block, we've turned these supplies on, which means at time 0, these two supplies are going to be on. Now, the interesting part is we saw other supplies, and these supplies were going on, off, and they could start off being off. And how do we model that? So on your test bench driver side, you would have to write a small state machine that goes through all different combinations. So in this case, note the system clock, power on, reset, these are not necessarily controls. These are what you define in your test bench. So these are your power supplies to your chip and your PMU or model or whatever your off-chip driver. And this is what we're trying to build right now. We're trying to build a model that drives and controls and programs the external supplies to your chip. And this example kind of captures how we're doing that. You're kind of specifying the exact voltage that you want, and you're also using a sort of state machine to model when you want to turn off. So that kind of is a simple example for how to build an SoC bench UPF.
My subject can be talk about what's coming inside UPF 2.1. 2.1 will have a lot of information, new syntax, new concepts because of time constraint. This is the slides of my presentation.